Well, in these sections, let's move on to decide the location of the neutral axis. And here the neutral axis, again, if you recall the previous materials, and that the fiber DE and locate in the neutral surface and interactions of the neutral surface with the cross sections, and this one here that's called the neutral axis. Okay, in neutral axis and or neutral surface is where the origin of the coordinate systems placed. So and that one in terms of symbol, that is where the rho, the radius of the curvature here is. Okay, and here we're going to base upon these equilibrium equations and to decide the location of the neutral axis. And if you recall in the previous sections, here is the 6 equations. Here we have, I'm going to use this one only, and this one basically saying that is the surface integral of this reaction, which is the stress in x directions, and that must be equal to 0 because externally we only have moment applied, we don't have any force externally applied in the x direction. So any reaction, that summation together must be equal to 0. So look at this quantity here, and E is a constant, rho is a radius of a curvature, that is a constant, although it's unknown yet, but this is a constant. So basically here this equation can be equivalent to this one. This equation is simply saying if we would place the origins in the neutral axis from where y is measured, then this integral is equal to 0. On the other side, if you recall what you learned from the statics about the centroid, if we measure the centroid, the distance y measured from the centroid, then over the surface integral of this quantity on that cross section, that is also equal to 0. So put the two things together, that tell us the origin is at the neutral. Sorry, the origin is at the centroid. Then the origin at the centroid, the origin locates in the neutral surface. The neutral surface interacting with the intersecting with the cross section to form the neutral axis. So that is saying the neutral axis passing through the centroid of a cross section. Okay, so the neutral axis must pass the centroid of a cross section. That is the take-home message here. So based upon this equation, that allows us to calculate the location of the neutral axis. And so here is the review from what you learned from statics. For the common shape, the centroid is for triangle is 1/3 of the whole height measured from the bottom. For rectangle, that's located at the geometric center here. For semi-circular shape, and the location of the centroid is y bar 4r over 3 pi. And how about for this case? This is kind of the composition of simple geometrical shape to form a cross section. This kind of T shape is pretty common in the beam, taking the loading. Okay, and of course we have other type of the shape. So basically the formula decide is using this formula. Okay, and or basically based upon this one. This one can be a simple version for simple geometry, can be in this way. So basically this equation is determined by this. The first one, you decompose into simple shapes, for example 2 rectangles. Then you identify easily for each rectangle that is the geometric centers of the shape, and that is a centroid where this rectangle 1 is, the same way the centroid of the rectangle 2 is. Then you pick the datum for your measurement. So here I pick the bottom face, the bottom side as my datum for measurement. From there, I measure the distance of the centroid, Y2 and Y1 bar, okay, and then from here, I put into this formula to calculate Y bar. Y bar basically is a centroid of this T shape, okay, and A1, A2 are the area of this, the portion 1, portion 2, okay. So once you determine the centroid, then that is where we place our coordinate systems. And in this section, the Z is the neutral axis, okay, representing is a neutral axis in terms of the three-dimensional model, okay. So let me draw that again. So this is our neutral surface. And intersections of the neutral surface with our cross section, this one is we call the neutral axis. And here in our placement of the coordinate systems is this. Y is in vertical direction and X is in the longitudinal direction, and the Z basically is in aligned to the neutral axis, okay. So here is one example here. So considering this shape, and we have all the dimensions here, and then here I pick the datum, the bottom as a datum for measurement. So first one I decompose into two simple shapes, the rectangle 1, rectangle 2. Then I individually identify the centroid for 1 and 2 here. And I pick the bottom as the datum for measurement. So this one is Y2 bar is 20, and this one Y1 bar is 50. Okay. Then I tabulate the calculation for area 1, this rectangle, the area equal to this, the area 2 equal to this, and that is the individual measurement for area 1. For the rectangle 1, the Y1 bar is 50. For rectangle 2, the Y bar 2 equal to 20. So I multiply 1800 by 50 equal to this. I multiply 1200 by 20 equal to this. And then I take the summation of the two numbers here, okay, and I put into the formula. So that is determining Y bar centroid location is 38 millimeter above the datum. So that is where this one Y bar equal to 38. Okay, so that is where we place the neutral axis, the Z axis and Y axis here. This is another example here. So basically this is kind of the I-shaped beam, and I decompose into 1, 2, and 3, the top flange, the bottom flange, and the middle rib, okay, and put into 1, 2, 3, and here you can exercise by your own, and then to try to see whether you can come up with this 4.778, and that is measure from the bottom. And again, for this exercise, I still take the bottom as the datum for my measurement, okay. And this case basically is the situations that is the beam, and later we will have continued this example to proceed the other calculations.